We are going to do some more problems on finite fields before we complete that session. The next problem we are going to do is let P of x be an irreducible polynomial in Zp of x for some prime p. Meaning you cannot factorize in this one into a polynomial of lower degrees of p. And let the degree of p of x be n. So then there exists an extension, let us say Zp prime of Zp that contains a 0 of p of x. Let us take a 0, we'll take alpha as p of x. Contains a 0 alpha of p of x. So actually what is then Zp of Z is equal to Zp of alpha, simple extension. And the irreducible polynomial, the degree of, or you can say alpha comma Zp is equal to p of x, and the degree of alpha over Zp is equal to n, because the degree of the irreducible polynomial is n. What does that mean? That means the degree of Zp of alpha over Zp is equal to n. And that implies Zp of alpha contains p to the power of n elements, and are precisely and the elements are precisely the zeros of x to the power of p to the power of n minus x. And that implies p of x is a factor of x to the power of p to the power of n minus x. So what we are going to prove is, what we proved is, every irreducible polynomial in Zp of x is a factor of x to the power of p to the power of n minus x for some n. And that n is the degree of this irreducible polynomial. We'll do another problem. Let f be a finite field of p to the power of n elements for some prime p and integer n greater than 0. Then definitely f is an extension of Zp. We know that. Now let alpha belongs to f be a generator of the multiplicative group that is of non-zero elements from f. So this means that Zp of alpha is contained in f, and f star is generated by alpha. That implies Zp of alpha is equal to f. And that implies the degree of f over Zp is equal to n. And that implies degree of alpha over Zp is equal to n. So if f is a finite field of Pn elements, and alpha is a generator of f, then the degree of alpha over p, Zp is n. So if f is a finite field of order p to the power of n, and alpha is a generator of f star, meaning the non-zero element of f with the multiplication as a binary operation, then the degree of alpha Zp is equal to n. See, whenever you say f is a finite field of order p to the power of n, it automatically it's the extension of Zp. So this implies actually there exists a irreducible polynomial in Zp of x of order n that has alpha, the generator, as a 0. Now we'll do another problem. Let E be a finite field of p to the power of n elements. See, for a p, we have finite elements p1, p2, p3, p4. That's that. But let us call the fields as E1, E2, E3, E4, etc. Probably for a prefix p here. These are all fields, finite fields of p1, p2, p square, p cube, p4 elements. But that doesn't mean that, see, this has got, for example, let's take p is equal to 2. Then E21 contains 2 elements, and that is actually CP, C2. E2 contains 4 elements. E3 contains 8 elements. But the question is, this actually contains 4 elements, this contains 8 elements, but this need not be an extension of this. This is of course an extension of ZP, but doesn't need to be extension of this, though it has 8 elements and 4 elements. So this problem shows a condition for which you will have a subfield of this order, a subfield in this sequence. So E be a finite field of p n elements, and m divides n, meaning m is a factor of n. Then we have another field E prime having p to the power of m elements. The condition here is m divides n, and the elements are elements of E prime are precisely the zeros of x to the power of p to the power of m minus x, and that is in Zp of x. Now let us take an element here. Alpha belongs to E prime. What does that mean? That means alpha to the power of p to the power of m is equal to alpha, or minus alpha equal to 0, and that implies alpha to the power of p to the power of m is equal to alpha. But m divides n. M divides m. This is m divides m. Or I will write it as m divides n. So m divides n implies there exists a Q such that n is equal to mq. M is a factor of n. So let us calculate alpha to the power of p to the power of n, and that is equal to alpha to the power of p to the power of n cube, m cube. But alpha to the power of m is actually alpha. So this is equal to alpha to the power of p to the power of m plus or m cube plus m or m cube minus m plus m. I am adding and subtracting m, and that is equal to alpha to the power of p to the power of m of q minus 1 plus m. And that is equal to alpha to the power of p to the power of m q minus 1 times p to the power of m. That is how you add it, right? And that is equal to, I am going to write it as alpha to the power of p to the power of m times p to the power of m q minus 1. And that is equal to alpha to the power of p to the power of m to the power of p to the power of m q minus 1. And this is alpha, and that is equal to alpha to the power of p to the power of m q minus 1. So we started with the mq and we arrived at mq minus 1. So continuing this, continuing the reduction on q, we have alpha to the power of p to the power of n is equal to alpha to the power of p to the power of m, and that is equal to alpha. And that implies alpha is a, alpha belongs to, or alpha is a 0 of x to the power of p to the power of n minus x. We started with alpha in E, which is a 0 of x to the power of p to the power of m minus x. And we arrived at this. And that implies E prime is a subset of, some subfield of E. So the result is, if E be a finite field of p to the power of n and m divides n, then we have a subfield of E having p to the power of p to the power of m elements. So this implies for a field of p to the power of m n elements, there exists a unique subfield of p to the power of m elements if m divides n. We are going to do one more problem in finite fields. This is going to be our last problem in this session. So let us define the problem. So let P be an odd prime number and A is an integer with A is congruent to, not congruent to 0, mod P. Basically, what does it mean? What it means is if P is equal to 7, A cannot be in 7, 14, 21, etc. That's what it means. Then we are looking for a solution x square minus a in Z. Can we have a solution always? Or if not, what is the condition for this polynomial have a solution in Z? In terms of P. This is purely in Z. So we want to find out a condition in terms of P, or what is the relation between A and P so that this polynomial has a 0 in here. So let us see what happens. So x square minus a has a 0 in Z if and only if x square minus b has a 0 in ZP for A is equivalent to B mod P. That is obvious. Now, ZP star is a cyclic group of order P minus 1. And that implies for any B belongs to ZP, B to the power of P minus 1 is equal to 1. Because it's a cyclic group of order P minus 1. Now, x square minus b has zeros in ZP if and only if b is a square of an element in ZP. If it's not a square, then there is no 0. And that implies B is an even power of any generators of Zp star. See, Zp star is a cyclic loop, so it's called a generator. So if an element has to have a square, that generator has to be a even power. And that, what does that mean? That means b to the power of p minus 1 by 2 is congruent to 1. Then only if you take the power, it is still b in Zp. So that implies, as if and only if, see, this is, we are taking b in Zp. So this is equivalent in saying a to the power of p minus 1 by 2 is equal to, or is equivalent to 1 mod p. Because this b is in Zp, this a is in C. So if you want to have a solution for x square minus a in Z, the condition is that a to the power of p minus 1 over 2 is congruent to 1 mod